in the lockdown, with the lockdown conditions? Is everything running? And actually, is someone staying in the university dormitories? Are they open? Mm. Okay. So last week, did you all connected to the seminar which followed the first lecture? And did you meet Ondřej Kurkin? Okay, so I heard you started with plant simulation, and so you got the first assignment. I heard that the results, some of you were really good, so that he got first responses in 1 hour. So it looks like it worked well, and I hope you will successfully continue today. You will receive the optimal version of the solution of the first assignment, and so you will receive first points. So as I said last week, you can receive 50 points from the assignments, and for the plant simulation part, you can receive 20 points. So you will receive the first point. I don't know exactly how many points you will get from which assignment. You have 4 plant simulation tasks to solve, and so you will get approximately 5 points from each. But maybe from the first ones you will get less because they are less demanding than the later ones. Okay.
So I have a question.
Yeah.
Is there somewhere a recording of the seminar? Because I couldn't participate because I was kicked from these teams, and I'm new to this team, so I have no idea whether it's recorded somewhere or not.
It should be possible to replay it in this team. It's automatically recorded, as I was told before the term started. So I think it's on the main page of this course in Teams. There is a record of the first lecture and also of this one. So
I don't see it there, but I guess I have to Google it how to do it because I'm really new to this, so I have no clue.
I didn't check it in this team, but previous term I was also using Teams for the distance teaching, and there was this record automatically saved and possible to replay. So I will check it. Yeah.
Okay, somebody just sent me a link, so
good.
Thank you.
Okay, so 5 minutes after the beginning, and so we can start now. I didn't manage to cover all stuff I wanted to speak about. So I will mute Ondřej Borovec. No, he's muted. He muted himself. No, not yet. Good, he's muted now. So I will continue with additive manufacturing. I just very quickly opened that topic, but I didn't have time to talk about additive manufacturing 3D printing properly. So what I said was that the 3D printing is not important only for production of final product itself, but it's very important also for printing equipment that is then used for later production. So typical products that are printed or created by 3D printers are some fingers for precise manipulations by robots, some equipment that helps with assembly of final products. Some forms you can use for molding processes and so on. The important thing is that you can use it for fast prototyping, because you can very promptly create the new version of product. So I brought an example which we worked on approximately half year ago during the first Corona crisis, when we used 3D printers to design, prototype, and then also produce protective half masks. Here we can see actually the progress we did in 1 week. So 7 versions of masks in 7 days, and the last one was ready for certification by the certification authority. Why I'm talking about this is that the possibility to create physical products and test it in normal condition, to put it on your face, is something that's still irreplaceable by simulation. So although there are many mechanical simulators that can visualize some strength and some tensions in products, it's difficult to create exact physical simulation that can show how something is elastic, how two bodies interact between each other, how it can fit to a face of specific type. So the possibility to create real physical product, change the thickness of layers in some parts, is something that's still much easier having the physical product in hand in comparison to simulations. So, and we used for that Hewlett-Packard printer, which uses technology called multi-jet fusion process. Here are some pictures illustrating how such process works. At the beginning, there is dust, plastic dust, that's used as an input material for the printing process, and from the storage of the dust, you can see on the left-hand side of the picture here, in the zone C, there is a storage of this material, and there a special piston pushes a thin layer of this dust into the printing area, which is here. So the thickness of this layer is about 1/10 of millimeter, and when this thin layer is placed to the printing area, then the printing head A uses so-called printing agents, which are based on ink, and prints this ink into the positions, into coordinates where the final products should be finished. So after application of this printing agent, then thermo printing head is used. Energy radiation energy is used, and the places, the spots where the printing agents were used, which were dark. These points absorbs more energy, and the plastic dust is melted, and then when it's cooled down, it changes the structure into solid material. Yeah, and after this, the process continues with a new iteration. So another thin layer of the printing dust is added to this printing area. Actually, this F piston, the bottom of this printing area, goes down about this 1/10 of millimeter. Then the new layer is applied, and again the printing agents are used. So dark color is printed in the areas where the final product should exist, and then again energy is applied, and this continues for a couple of hours, and at the end you have a container full of dust, but not only dust, but also full of the printed stuff. So you have then to use kind of vacuum cleaner that absorbs the dust, that can be then reused again, and you get from this container of dust the final products, which you have to clean, get rid of the dust, and the product is finished. You can also do some post-processing. You can color it, but it's not necessary. Okay. So the last important part of Industry 4.0 is usage and utilization of augmented reality. So for design of new production lines, estimation of impact of some changes in production area on the other processes, it's quite useful to be able to see the new equipment as it was physically present in the considered area. So augmented reality enables to combine the real view, or the view on the real space, with some added objects. So, for example, you can place a 3D model of a robot into an existing production hall, and see how it fits into space. You can verify that it doesn't collide with some other objects in the area before you physically install this device into the factory. What's also quite useful is to use augmented reality to project some sensoric data about real machines to the view of the operator. So operator can see a virtual dashboard when the operator looks at the physical device. So it can check some parameters, temperatures. He can see some description of the orders, the tasks that the device is currently working on. So this is another possible application. So in testbed at CIRC, we did some experiments with HoloLens. Actually, the very first version of the testbed used the combination of the real physical equipment with some projected parts, depicted via HoloLens technology. Actually, the reason for that was quite simple, because at the beginning, when we designed the first version of the production line, we didn't realize that the load capacity of the floor in testbed is limited only to light equipment, and so the heavy machines wasn't possible to place into the intended area. So the heavy machines had to be placed downstairs, but the use case that was planned actually needed to have all the machines connected, and they were participating on a common production. So the solution was that the light machine as well as the heavy machines run in parallel in different locations, and they were synchronized via process simulation application. But the important thing is that actually the current state and the current operations of the heavy machines were projected via HoloLens to the visitors of the upper testbed. So we could see. Pardon. Someone forgot to mute his microphone. Okay, so we could see cooperation of real and projected robot via augmented reality. Currently, we are experimenting with the Fata Morgana application, which enables remote presence of operators in remote areas. So please look at this video that explains how what the potential of this remote presence in industry is.
Ours is a revolutionary way to share remote locations, interact with distant workplaces, and with your colleagues who share them. All of this is possible in real time. Furthermore, its versatility allows for applications across a wide variety of industries. Our software facilitates private and secure communication using AR and VR headsets. On-site employees scan the physical environment, which is then transferred to our servers where the data is processed. Then the environment can be shared by off-site specialists. In the shared VR environment, a variety of tasks can be performed with an intuitive and user-friendly interface. Copy and paste high-resolution images and videos. Compare, measure, and interact with real-world objects. Take notes, write messages, track tasks, and chat with colleagues. Select, insert, and compare blueprints and 3D models. Remote coordinators manage, monitor, and record user activity. Holographic tables offer a perfect overview of communications in the shared virtual environment. Fata Morgana has tremendous potential for use across all industrial sectors and a long-term vision. Our goal is to reach a wide range of users and ultimately become the global leader in AR and VR remote presence technology. All technological displays, including the holographic table, are functional and authentic. The FM platform is field tested at the Temelin nuclear power plant.
So, the important thing about the Fata Morgana product is that the sensors that are present at the HoloLens device on the head of the operator that is close and physically present in the area that we deal with. So the power plant in this demo or in our testbed, that the sensors actually are used to create a digital model, 3D model of the area. So you don't need to create in front this application, the 3D model, and then use it for the remote expert, and you don't have a static view on this area, but the view is dynamic. And actually, what the frontline operator sees, this is immediately transferred into 3D model, and the remote expert that doesn't use augmented reality headset but virtual reality headset actually sees also not only what the frontline worker sees, but also the models, the 3D scene where the frontline worker is located. So such a system is very versatile, very flexible, and very easy to use. So in these days, it's quite important to have these possibilities because many factories are closed for preventive reasons related to COVID issues, and some, for example, we are using this and we experimented with this Fata Morgana system within our project with Lego company. When we needed to have some visual feedback of equipment, we are controlled via our AI approach, and we needed to see actually how it works. Normally, we would be present to the production line to have the direct feedback, but it's not possible in these days. We aren't allowed to enter the production because of quite strict rules coming from Denmark. So we are using this HoloLens technology to see, at least in this way, what are the reactions of the counting machines we are working on to the new versions of the control system we developed. So quite useful and easy to use system. Okay, so the last thing I want to speak about in this Industry 4.0 introduction is big data and data analysis. Data mining and data analytical methods are quite well known and developed not only for industry but for many other domains. What's quite specific for industrial systems is advent of process mining methods. So to identify what processes are running on the shop floor, to be able to interpret the system logs into some models of discrete events. So within our testbed, we are using the process mining tool Chrome, which is connected to OPC UA communication and used open XES format for data logging. So when we saved the events that happened on the shop floor in this format, and the events are like that the machine was switched on, it did certain operation, or it measured certain values from the sensors. Based on this, we create process graphs, and process graphs should look like could look like petri nets, a model, discrete event model that explains what are the individual states and their connection of the system. And based on this, the system detects the typical processes that happens on shop floor, and then it's very easy to be used for deviation detection. So when certain process changes the typical scenario, this exceptional behavior can be highlighted and shown to the operator that an uncommon behavior was observed. This is an example of the OpenXDS data log, and explanation of what I've just said, how it can be used to predict the deviations in the behavior observed by the system. Okay, so the Industry 4.0 test beds are important part in the transformation of the industry from the traditional system into ecosystem of interconnected subsystems. It's necessary to be able to play with physical equipment, to test new algorithms and new ways how the traditional systems can be controlled. It's important to have such facility to be able to connect research with industrial practice, to create real demonstrators and inspire the technicians and make new approaches alive. Okay, so we went through all this, and this is the end actually of the first introductory lecture what I wanted to cover during previous week. So let's close this. I will share all slides with you via Teams, but also Moodle. And let's.
Could I interrupt for a second, please?
Yeah, sure.
It's not really related to what you were just saying now, but I just see that in the English Teams, somebody else is complaining that he cannot access the Czech ones.
Okay, so thank you. I will send the link to the Czech one. I checked that all the students from the English team are added. I added them manually last week to the Czech version, and let's check it. David is a new student. So unfortunately, I can't see him connected yet, but David was added, so hopefully he will be able to enter this team. Okay. So I hope no one else is left outside this Czech team. So let's continue with the new topic. Or are there any other questions related to the first lecture about introduction of the Industry 4.0 transformation? If not, we will start with Petrinet. Actually, we just briefly mentioned the Petrinet in the last topic related to Industry 4.0 to process mining, where Petrinets were output of the process miners and represented a behavior of a system of discrete events. So Petrinets are models of discrete event systems. They can be or they are typically used to model behavior of parallel systems. So some systems that have that can contain more processes running in parallel, and parallelization can cause some problems. So using Petrinets, we can detect the possible problems, some deadlocks, for example, and try to change the system in a way that deadlock cannot occur. Also, typical application of Petrinets is modeling of distributed systems, and it's closely related to the parallel nature of such systems. So it's not very new. Formalism, it was proposed in beginning of 60s by Karl Adam Petri. That's why Petrinets, and it was presented in his PhD thesis, Kommunikation mit Automaten. So it was closely connected to usage of the first PLCs, programmable logical controllers, to control production systems. So at that time, it was necessary to be able to guarantee some kind of reliability in communication with these industrial computers, and the Petrinets were adopted quite promptly, and receives a lot of attention. Then talking about PLCs, actually, do you know, does anyone of you know GraphSet? GraphSet programming language for PLCs? If not, doesn't matter. It was a quite popular approach to programming industrial computers, PLCs, especially it was very popular in the French community in automation. The notation and the way of description of the programs is very inspired by Petronet. So if someone knew GraphSet, then the Petronet would be familiar to him. Anyway, so Petronet is a bipartite-oriented graph. Actually, do you know what bipartite-oriented graph means? Bipartite means that there are two types of nodes in such a graph, and the link can be always done only between nodes of different types. So you can connect with a link with edge two nodes of the same type, and the types of these nodes in Petronet are so-called conditions, C nodes, and events, E nodes. And the arcs, the edges that connects these nodes are oriented. So there is a direction saying which node is the source and which node is a target. And the important thing is that the number of both type of nodes is finite and is greater than 0. So we need to have at least one of this node in every Petronet. Otherwise, such a graph isn't Petronet. So let's start with the basic concept which is behind Petronet. So another thing how to model and capture behavior of a discrete event system is state automata. So in state automata, each state represents a particular state of a system, and the edges represent the possible transitions from one state to another. In Petronet, the state is represented by marking of the whole Petronet network. So here the marking on the left-hand side, where the black dots are placed in the center of nodes P1 and P2, represents the state 1, the initial state, which is then transferred into state 2, which is represented by the marking with active nodes P3, P4, and P5. The important thing here is, and coming back to the state automata, is that for more complex systems, we can express much more states of the system with lower number of nodes. So because we can use the combinations of the tokens in here, and we use this we use the state of each node, and all the combination of the states represent actually a new state. We can, with much less nodes represent the same number of states compared to the state automata. So at the end, the more complex systems that are captured with Petri net notation are less complex than it would be using the state automata approach. Okay, so so the very first type of Petri nets proposed by Ilan Petri was CE, condition event Petri nets, when one type of node corresponds to conditions and the second corresponds to events. But then different versions or various versions of Petri nets were derived from the basic concepts. So now we can meet PT Petri nets, place transition Petri nets, time Petri nets, curled Petri nets, and so on. So let's start with the CE Petri nets. So in a CE Petri net, the conditions correspond to nodes represented by these circles. So we have two conditions here, and one node, this rectangle, correspond to an event type of node. This is it. So we have one condition, and event in between. And these nodes are connected by two arcs. Inside a condition node, there might be a token. It can be there or cannot be there. In CE Petri nets, it's 0 or 1. So only two possible states. And the tokens or the nodes that the condition nodes that has an R coming from them to an event node are called preconditions, and the outputs from an event condition nodes connected to the output of the event are called postconditions. So, as I said, each condition is either true or false. True as a token inside, the false is without token. In the global state, of a net is defined by a set of true conditions. So the positions of these tokens correspond to one particular state. S0 is used to denote initial marking, and the behavior of such a system is controlled by two rules. The first is enabling rule, and the enabling rule says that all preconditions are true. So all nodes that are connected to an event has a token inside. So and all postconditions are false. So all the output nodes are ready to absorb a token. So nothing is in the output condition nodes. And the firing rule says that after an event is so-called fired, then all preconditions are false, so the tokens disappears basically from the input nodes, and all postconditions are true. So the tokens then appears in the output conditions. So if an enabling rule is met, it's possible to fire an event, then the consequences of this operation are defined by the firing rule. There are also some special e-nodes. In this case, where the event node is not connected or doesn't have any input, this node is called source, and it's like a pool source of tokens. It can anytime. It's like there was an e-node that was always true. So the conditions, the enabling rule is always satisfied, always met. And similarly, the sync special e-node is always ready to absorb a token. So it's the same as there was a token, a node that was always without a token, so always ready to absorb new token. So what about such a situation? What can be the output of this situation? So what are the enabling is the enabling rule met? Or actually we have two event nodes here, left and right, and we have to validate the rules for each node separately. So is the enabling rule for this event met? Yes, it is. So all the input nodes are true, and all output nodes are false. And what about this one? Again, the same. All inputs are true, all outputs are false. But in this case, it depends in what order we fire these events. So actually, we can fire only one event, otherwise, because then the enabling rule doesn't hold anymore for the second event. So there are two possible outputs from this state. The first is that the left event was activated, and this is the output. Now we cannot activate the right event anymore because in P2 we don't have a token, and the enabling rule isn't met. Or we activated the right event when we could, and then the left cannot be activated anymore. So this situation is called a conflict. So we have a structural conflict in this pattern net, and it means that the behavior of this system is not deterministic. It depends on the order which is not defined by the structure of the net. As I mentioned, GraphSet programming language for PLCs, it would be this behavior for programming language for a PLC would be a big problem. So in automation, the determinism is very important. So you don't want to have an undeterministic production line because it could cause many problems. So then in graph set, and one of the big deviation and differences between Petri-nets and graph set is that in graph set there is a rule that you start you apply the rules from the left to right. So in the graph set, the behavior would be deterministic because this condition would be tested as first one, and so the only result of this state is the upper one, because the left transition was activated as first. In Petri-nets, this leads to conflicts, and you can't say, based on the structure, you can't say whether the output is the upper one or the down one. So finite automata is a special case of the C Petri-net. So finite automata, you have some states defined and the transition between them, and you can, every finite automata you can very easily transform into notation of C Petri-nets. So 4 states, 4 transitions. There are special constructs sometimes used in Petri-nets. Elementary loop. Elementary loops are actually or depict the situation where you have one C node, one E node, and the R's coming there and vice versa back to it. So there, even if you conduct the transition, actually the output of the output of the first state is the same as the previous one. So it repeats the steps in an infinite loop. It's important to say this because if you don't have these elementary loops in a Petri-net, then it's poor, and you can assume some behavior you can't do if you allow elementary loops to have present in Petri-nets. So the pure Petri-nets doesn't contain any elementary loops that can cause some problems in validation of the behavior of such a network. And another category or subtype of C Petri-nets is elementary Petri-net. So it's every event has at least one precondition and at least one postcondition. So basically there are no sink nodes or source nodes, and it's also poor. So it doesn't contain elementary loops. So with some basic building blocks, you can create more complex systems, more complex programs. So one-shot elementary program that system that does only one step is elementary program, and is depicted like this. Never-ending elementary program continues never-ending loop, and can be expressed like this. So sequence of events looks like this upper picture, or the iteration where we iteratively do an event is depicted on this bottom picture. Here, notice the difference between an alternative and parallelism. In alternative, the process goes through one event or another event, but continues as one single process. In parallelism, there is again a fork, but the fork doesn't start in a condition node, but it starts in an event node, and it means that one process is forked in two processes that can run in parallel, each with different pace, but then they are connected again here with this node. But it's not necessary that in parallelism also can this join here is not necessarily present in parallelism. But the difference is that this event can occur in different time than this event. So the speed in the upper branch and the lower branch can be different. What may be the most important thing for and the strongest motivation for modeling system with patterns is our models of synchronization. When you need to prove that parallel processes can synchronize as intended, can and don't get in some deadlocks, then you model the system in a way that you can explicitly see the synchronization elements and analyze them before in the model and not afterwards when the basic principles of the behavior of a system cannot be can be hidden in the complexity of the digital system. So synchronization of two processes. The process one synchronize with this process two with a construct called semaphore. You might know it from programming courses. The semaphore is used that one process provides a signal to another process that the second process can continue. So this construct is called semaphore, and this and actually the process here, process two, is controlled by process one. On the right hand side, the processes one and two are equal, and this construct says that the one process, the first process as well as the second process has to wait for the other process. So they can't continue the processes without meeting at this point, and when both processes get to this stage, then they can continue. Otherwise, they have to wait for each other. And this concept is called rendezvous, and again, quite widely used in programming of parallel systems. So if we have a critical section somewhere, so for example, we have two robots that want to share, or two robots that share a common workplace. We can lock this workplace with a critical section. It means that only one robot can enter such an area at one time, and this is called critical section. So either process one continues with the next step, or process two continues with the next step. If we add one more condition node to the system, we can guarantee that the processes regularly alternate between each other. So the situation when the tokens are coming from this source, and we get token into this condition node, we can activate this event. And then when this event is activated, we got a token in here, token in here and in here. And then it means that the process one, it's turn of process one, and the process one can continue. And this construct guarantees the regular alternation. So if this notation is used in the graph set node for programming automated system, quite clear we can prescribe the behavior as intended in terms of synchronization of two processes. And what about this? The only difference from the previous situation is that we don't have a token in here. Do you know how this state is denoted? I'm quite sure that if you ever programmed a parallel system, a system with multiple subprocesses, you experience this situation, and the situation is called deadlock. So the first process one waits for a token coming from process two, and process two is waiting for this event. And when two processes are waiting for each other, the situation is called deadlock. PT-Petri-net is a simple and straightforward extension of C-Petri-net. The definition is a 6-tuple where P, T, and F defines a finite bipartite oriented graph. The vector W adds weights to the arcs. Vector K adds integer numbers to P nodes and represents the capacity of the P nodes. And M0 is the initial marking, and it says where the tokens and how many tokens are present in each P node at the beginning, before the system represented by such a PT-Petri-net start its behavior. So difference is that so this time in P node we don't have 0 or 1 but any integer number, and to express the state we use markings, and this marking here the state of this Petri-net. The marking 0 is 1 1 0 0 0. So here is the vector of the P nodes, and the values correspond to the number of tokens in every P node. Here the marking 1 is describes the output state. So the marking defines the state of such a network, capacity of a place. Here the capacity can be bounded to an integer number, so it can be bounded to number 2, for example, or unbounded, so unlimited. And weight of an arc, it says what is the cardinality of the connection. The default weight is 1, but it can be increased. And we will get to that later. So again, even in PT Petri-nets, we have a special nodes, source and sink, very similar to the CE Petri-nets. The important purpose for having PT Petri-nets is that we can formally analyze the system that is described with such a Petri-net. So key characteristics that we can derive from a Petri-net model of a system is detect whether the system has the property of liveness, that it's live, so it means that it doesn't contain any deadlock, that it's conservative, or that it's safe, and boundness. So what does it mean? So the liveness solves the question whether the system dies in any particular state. So it means that in every state there is always a live transition, a transition that can be conducted, and there is always a possible action that we can do in such a system. So the question is that can a live net have a deadlock? I said not. The safeness is closely related to capacity, and a place P is safe if for all markings the marking that is derived from the initial marking has marking of the P node less or equal to 1. This symbols expresses that a marking, some marking M is derived from marking 0. So it doesn't mean that it's the direct successor of marking 0, but it has the marking 0 somewhere in the ancestors of the row of marking. So we can, if this is written like this, it means that for marking 0 we can get to marking M. In marking M, the value of P is less or equal to 1. And finally, if we define what safeness is for one P node, we can define the property safeness for the whole network, and Petri-net N is safe if for all P for all places in such for holes that they are safe. So marking, actually, if the network is safe, then it looks like a C Petri-net. Again, the markings and the number of tokens in a safe Petri-net is 0 or 1. So what do you think? Is this network safe? Is it guaranteed that in none of the places can be more than 1 token? No, because from here this is unlimited source of tokens, and arbitrary number of tokens can come to this place. But how to make? What if we need to guarantee that these places are safe, so there can be more than 1 token? We can add some additional places, for example, like this, and this additional places guarantees that we can't get more than one token in this node, and the same holds for this. So using this additional p nodes, we can change the property of the whole network and change it from unsafe to safe. Boundness. So it's a property that solves the question, will a storage place overflow? So is it guaranteed that there won't be more tokens, units of material, whatever, greater than some limit? So assume we have Petri net defined by this vector, and we say that place P is key safe if for all markings that we can derive from the initial marking 0, holds that the marking of every of this place P is less or equal to key. If the place P is key safe, then the P is bounded, limited by this constant. If all the places are bounded, then the whole network is bounded. So another important property of PT Petri nets is conservativeness. The first version of this conservativeness is strict conservativeness, and it says that if a network N is strictly conservative, it means that for all markings that are reachable from marking 0 holds that a summation of the tokens in all places are constant. So the number of tokens in any marking is equal to the summation of the initial marking. So the number of tokens remains the same, whatever happens. So the node, which is here, actually says that it's quite strong property, and the direct consequence of this is that, for example, the number of inputs and outputs of each transition node must be equal. So if one transition node has 2 inputs, it also has to have 2 outputs. Otherwise, the number of tokens would differ between the following states of the system. So the conservativeness, not strict, but just conservativeness, is less strict, and the difference between the strict conservativeness and the conservativeness is that we add to this condition weight vector W, and this weight vector W is used to transform the overall value of one marking to another one. So we will use an example. Normally, I would drive it an example on a whiteboard, but it can be quite complicated. There's also notice on whiteboard in Microsoft Teams, but it it's not that convenient to write on the screen. So I will explain the weight vector later on, because there are some slides that can be quite useful for explanation of this concept. So general comments. So pattern nets are good for modeling systems with concurrency and some synchronization aspects. And the tokens can represent available resources or jobs to be performed, synchronization conditions, or state of a process. So concurrency. The independent transitions enable concurrent firing. So this is one network. These both parts represent one network, and since there are no links between these events, they can be fired independently. Again, here the overlapping conditions. So difference is that there is this this link, and here we have structural conflict again, because we can fire any of these events at the beginning, but when the first transition is fired, the second one cannot be anymore. The same was with the C pattern. Mutual exclusion. So for synchronization, we can express how we can synchronize these elements. We can model fork and join. The one process can be forked in some subprocesses. Each continue independently, and then they are joined again. We can model producer and consumer pattern. So this process produces something which is consumed by the second process. This can be extended with the concept of bounded buffer. So we have some finite number of slots we can use, so 3 slots in this way, and when we use this slot, we have to wait, or this slot is in this state, and when it's received processed by the receiver, we get it back into the set of 3 slots. So here we can guarantee that the number of, for example, sent messages isn't greater more than by 3 between the number of sent messages and received messages. In complex systems, the graphical notation isn't the preferred way how to describe a matrix, because it's much more convenient than a state automata to capture structure of a complex system. It's even pattern nets can get quite quickly too complex to be understood by a human. So quite useful way how to do the analysis of systems captured via pattern nets is matrix representation of pattern nets. So if we have such a pattern net, and we can define an incidence matrix for this pattern net, and the incidence matrix has a dimension number of rows equals to the number of p nodes, place nodes, and the number of rows, columns, is equal to the number of transition nodes. And maybe I will directly jump into this example. So assume that we have, let's have such a pattern net depicted on here on the left hand side, and let's try to create the incidence matrix. So the incidence matrix is composed of input, output incidence matrix W plus and input incidence matrix W minus. And so in the output incidence matrix, we capture actually the impact of activation of one transition on the number of tokens in the whole system, the whole network. So here, as I said, the number of rows corresponds to the number of P nodes. So we have 5 P nodes from phi1 to P5. So we have 5 rows, and we have 4 transitions, P nodes. So that's why we have 4 columns in here. And then when we need to get the value into each cell of this matrix, we analyze what's the impact of the activation of T1 on these P nodes. So the first row corresponds to the impact coming from transition 1, T1. So if we activate T1, the possible impact on a number of added tokens into P1 is 0. So if this is activated, and now we don't bother with the conditions, the preconditions, but just if we can activate it, and if this is activated, if it's possible, then there is definitely none token added to P1. So that's why there is 0. But place 2 and place 3, there is 1 token added, and also into this P3 place 1 token goes. So that's why there is on the second and third row 1 and 1. And again, if you activate T1, there is no impact on P4 and P5. That's why 0 and 0 are on the 4th and 5th column, row in the first column. So similarly, we analyze the impact of activation of T2. Now we see that the possible contribution to the number of tokens is only for P4. So that's why on the 4th row of the second column there is 1. Otherwise, there are 0 on other places. T3 can add 1 token only to P5, and T4 it adds 1 token to P1. The contrary, the input incidence matrix W minus assess how many tokens disappears from a particular place token when a specific transition is activated. So if T1 is activated, 1 token disappears from P1. So that's why here is 1. Nothing else happens to the number, or no other token disappears from any other place. So that's why the 0 is here. If we activate T2, which is here, only token from P2 disappears. Nothing else happens. If we activate T3, only P3 disappears. And then the overall incidence matrix is created by combination of these two matrices, and actually it expresses what the overall impact of one of the transitions, of the individual transitions on the state of the whole network. So if we activate transition 1, it removes one token from place 1 and adds one token to place 2 and P3 and so on. So incidence matrix doesn't depend on marking. So as you saw, we didn't need to have any tokens here to do this analysis. It doesn't say anything about transitions in terms whether they are enabled or disabled. So we didn't solve any rules whether we can fire something or not. And coming back to the poor nets, if the nets are poor, we can reconstruct such an incidence, such a network from the incidence matrix. If there are some elementary loops, they don't appear in the incidence matrix. So that's why the networks that are not poor cannot be reconstructed from the incidence matrix. And important thing why we introduced incidence matrix is its combination or its usage in so-called characteristic vector, and this is something that we will start with next week, and we will show how we can compute the future states of a system, combining incidence matrices with characteristic vectors, and how we can predict what are the possible states of a complex system using only this mathematical or algebraic operations without need to do it manually and graphically. Okay, so any questions to this topic, or any other questions in general? So if not, so let me close this lecture and hopefully meet you here next week. So thank you for your attention and see you next week. Bye.